All right, chapter 8, 6 is called probability. So we're going to divide this into two parts. Today's part 1, obviously. Probability basically is an extension of what we talked about in the last section. So in the last section, you were working on how many different ways something can occur. Now we're going to talk about what's the probability that a single event within those events will occur. Okay? So you're talking about chances here. Percentage, not percentage, a fraction that represents the chances some will occur. So just some vocab on this slide. Any happening whose result is uncertain is called an experiment. So rolling a die, flipping a coin, those are all experiments. The possible results of the experiment are called outcomes. So if you're flipping a coin, it could be either heads or tails. The set of all the possible outcomes of the experiment is a sample space. So if you are flipping one coin, then your sample space is either heads or tails. And then any sub-collection of the sample space is an event. So let's say you wanted to get heads on your flip of your coin, then that would be your event. For instance, when a 6-sided die is tossed, the sample space can be represented by the numbers 1 through 6. And then an event would be rolling a 2, something like that, okay, or an even number. For the experiment to be fair, each of the outcomes is equally likely. So we are assuming that there's a 50-50 shot at getting heads or tails. We are assuming there's a 1 in 6 shot of rolling a die. If you're pulling from a deck of cards, 1 in 52. Okay, so everything is equally likely in these scenarios, not like a weighted coin or anything like that. So example 1 just says to find the sample space for each of the following. So we're just listing what are your possible sample spaces out of these. The first one says 1 coin is tossed. So if a coin is tossed, what is the possible outcome? All right, so if you toss 1 coin, what are the possible outcomes? Heads or tails. That's your sample space. 1 heads or 1 tails. If you toss 2 coins, then what can happen? So you can get a heads both times. You can get a tails both times. You can get a heads and a tail, or you can get a tail and a heads, right? So one way you can check to make sure that you've got them all is think back to the last section. If I flip a coin and I flip a second coin, those are 2 separate events, right? Like if I flip 1 coin and a second coin, they have no bearing on each other. And so if I want to know the number of options that there are, I multiply the number from the first time by the number from the second time. So if I flip the first coin, there's 2 choices. Yes? I flip the second coin, there's 2 choices. I do 2 times 2, so 4. That's how I know I have all of the ones covered. Does that make sense? So if there's 3 coins tossed, how many choices are there the first time? 2. How many would there be the second time? 2. How many would there be the third time? 2. So how many outcomes am I looking for here? 8. So there should be 8 in my sample space. So I can say it is tails, tails, tails. It is heads, heads, heads. It is tails, heads, heads. It is tails, tails, heads. It is heads, tails, tails. Heads, heads, tails. What am I missing? Heads, tails, heads, and tails, heads, tails. 1, 2, 3, 4, 5, 6, 7, 8. There, I've got all. So this is generating your sample space. Okay, so the probability of an event occurring now is going to be represented by a fraction. If an event E has n of E, likely number of outcomes, and its sample space S has n number of equally likely outcomes, then the probability of event E is given by the number of the event you're looking for over the number of the total sample space. So in like regular English, it's the number of what you want over the total number of the sample space. An event is what you're trying to get. So if you want to figure out the probability that you're going to land on heads, then the heads is the event.
So in that case, what would be what you want?
The heads. So the event is what you want. And then the sample space is that if it's only 1 coin, it's tails or heads, so it's be 2. So because the number of outcomes in an event must be less than or equal to the number of outcomes in the sample space, you can't have more that you want than the sample space, okay? Then the probability of, and this should be an event, that should be a T, of an event, must be the number from 0 to 1, inclusive. So it actually could include 0 and it could include 1. The probability is 0 if it's an impossible event. If I said I'm going to flip a coin and I won a 2, can't happen. That's an impossible event. That's 0 out of 2, okay? If the probability is 1, then it's a certain event. If I am going to get a number by rolling a die, all 6 are numbers, that would be 6 out of 6, that's 1, okay? So it can't be less than 0 and it can't be bigger than 1. 0, impossible. 1, 100% likely. Certain event. All right, 2 coins are tossed. What's the probability that both land heads up? So we already have this sample space. We had tails and tails, heads and heads, tails and heads, and heads and tails. So there was 4 options in my sample space. Out of these, how many of them would both land heads up? 1. So it's just 1 out of 4. Remind me to go back to this one because when we get to the end of the notes, I'll tell you how you could also have done that differently. All right, B says a card is drawn at random from a standard deck of playing cards with the probability that it's an ace. So if you are not familiar with a deck of cards, you have to know the deck of cards. There are 52 cards in the deck of cards. There are 4 suits, 1 hearts, 1 diamonds, 1 spades, 1 clubs, okay, which means there are 13 cards in each suit. Half of the cards are red and half of them are black. So 26 are red, 26 are black. It is ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. If it's talking about an order like less than a number or greater than a number, it will tell you if ace is low or high. Ace is low means you're going to count it like a 1. Ace is high means it would be like an 11. Okay? And then there are 3 different kinds of face cards. So a lot of times you'll see face cards. These are cards that actually physically have a face on them. So these are jacks, queens, and kings. Aces are not face cards. There's no face on an ace. All right, so B says a card is drawn at random from a standard deck of playing cards. What's the probability that it's an ace? How many aces are there in my standard deck of cards? 4. And how many total cards are in my sample space? 52. This would simplify to 1 over 13. So just like every other fraction in this class, you will always reduce them.
Can you talk, what's the special thing about the face cards?
Face cards are jacks, queens, and kings. So some people like to consider a face card as an ace. That is not the case. It has to literally have a face on it. If you look at a jack, there's a picture of a jack with a face.
For 8, you said that it was 1 out of 4, so you wouldn't count the one where it's H, heads, heads.
That's the only one you count.
What about HT?
It said that both land head up, so you needed them both to be H. All right, mutually exclusive events. So 2 events from the same sample space are mutually exclusive when they have no outcomes in common. It is not possible for it to be both. So for example, a card being a 5 and a 6. A card cannot be both a 5 and a 6, right? It's either a 5 or it's a 6 or something else, but it can't be both. Those are mutually exclusive. If I said a red or a black, those are mutually exclusive. It can't be both, okay? The probability of event A and event B, if they are mutually exclusive, would be the probability of their overlap, which wouldn't exist. So if I said, what's the probability of getting a 5 and a 6 from your deck? Okay, it's not possible. There would be that wouldn't be possible if you picked one card, a 5 and a 6. Okay, but if A and B are mutually exclusive, where they are separate, then you add their individual probabilities. So these little symbols, this U means or, A or B, because that's an intersection. And this little symbol means intersection, where they overlap. So to find out if it's mutually exclusive, you would take the probability of the first one and add it to the probability of the second one. So if it's or, because this is going to change when we get to and. If it's or, we add their probabilities. This or that. Example 3 says one card is selected at random from a standard deck of 52 playing cards. What's the probability that the card is either an ace or a jack? So is the ace and the jack mutually exclusive? Can something be an ace and a jack? No. So these are mutually exclusive. So we're going to figure out what the probability of getting the ace is, and we're going to add it to the probability of getting the jack. How many aces are in the deck? 4, so this is 4 out of 52. How many jacks are in the deck? 4 out of 52. Okay, you can choose, because they both have the same denominator, you can reduce them and then add them, or add them and then reduce them. It doesn't matter. This would be 1/13 plus 1/13, which is 2/13. When it's an or, the odds should be better when they're together than when they were by themselves, right? If you're saying this or this, now you've added yourself another option that should be it should be easier to get. So obviously 2/13 is better odds than 1/13. Questions so far? Okay, not mutually exclusive means that they can overlap. So a red card and an ace, it can be both. That would be not mutually exclusive. Rolling a die, getting an even number and a 2, those would be not mutually exclusive. When you find the probability for those, you're going to take the probability of the first, add it to the probability of the second, but then subtract the possibility of the overlap. So if I had used the die one and I said even and even or a 2, then I would do the probability that you're going to roll an even die, an even number, plus the probability that you're going to roll a 2, minus the probability that you roll an even and a 2, which would be the number 2 itself. Otherwise, you double count it. The number 2 would be part of both even and 2. I can't change the odds. So this is when it's not mutually exclusive. So the first thing you're going to do is ask, can it be both of those things? If it can't be, then you add them. If it can be, you add, but then you subtract the overlap. All right, example 4. One card is selected at random from a standard deck of 52 playing cards. What's the probability that the card is either a heart or a face card? So would heart and face card be mutually exclusive or not mutually exclusive? Not, because it can be both a heart and a face card, right? So I'm going to do the probability of the heart plus the probability of the face card minus the probability of the heart that is a face card. So how many hearts are in the deck? 13. 13 out of 52. How many face cards are in the deck? 12. There's 4 jacks, 4 queens, 4 kings, right? So 12.
How do you figure out the probability, like the overlap?
So look at your face cards. How many of those face cards have a heart on them? If you look at your face cards, how many of these face cards have a heart? 3 of them, right? The jack, the queen, and the king of hearts. So minus 3 out of 52. So then this is 25 minus 3. This is 22 out of 52, or 11 out of 26. They might reduce differently. So I would say maybe add them or subtract them first and then reduce them. Questions so far? All right, independent events. So 2 events are independent when the occurrence of one has no effect on the occurrence of the other. This is similar to with replacement, right? If I start with a bag of rocks and I ask you what's the probability you pull a red one the first time, but then you put it back, that's an independent effect, because what happens the first time does not affect what happens the second time. If, when you pull the rock out and you keep it, those would not be independent events because now you've affected the sample space that's left. So if they are independent, which would be like rolling a die, generating a random number, flipping a coin, all those, once you do it whatever once, it's not going to affect the second time, then you find the probability of both independent events occurring by multiplying their probabilities. So now it's and. Before it was or, now it's and. So or is addition, and is multiplication. Is it harder to get two things or one of two things? Obviously both, right? So when you get an and, you're multiplying. When you multiply fractions, you make them smaller. You're making your odds less likely. When you're adding, you make it more likely. So example 5 says a random number generator on a computer selects 3 integers from 1 to 20. What's the probability that all 3 numbers are less than or equal to 5? So I've got my first number, my second number, and my third number. I'm going from 1, 2, 3, 4, 5, 6, blah, 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 blah. My goal is to get a number less than or equal to 5. So how many numbers are less than or equal to 5? 5. How many total numbers are my sample set from 1 to 20? 20. So the first choice is 5 over 20, okay? Now it's a randomly generated number, so those numbers are reset every time, which means how many, or what's the probability of getting the second one to be 5 or less? 5 out of 20. How about the third one? 5 out of 20 again. These I would probably recommend reducing. But then this is an and, so I would multiply. So 1/4 times 1/4 times 1/4, or 1 out of 64.
So your sample size would be 20?
Right, because you're going from 1 to 20. So you'll start to see some of this stuff mixed in. You're flipping a coin and rolling a die. What's the probability of getting a blank or a blank? And those you're going to add. What's the probability of getting a blank and a blank? And those you're going to multiply. Questions on what we covered so far? All right, so we'll finish 8-6 tomorrow, okay? But I want to spend the rest of the time, not the rest of the time, but some of the rest of the time, talking about your interview project. So if you go to Canvas and you go to the interview project module, we're going to talk about it.